Okay, we're going to be discussing homework 1, and which runs experiments for the KNN classifier on a multi-class problem. So we're first going to go through the code and see that it all works. So we've got our imports. We're uploading the iris dataset. We're breaking it up first into the 2 features data and checking our shapes to make sure that it is 2 features, which is the X2, and X4 is for the 4 features, and we're using X2. Here we're going through and we're doing our train test split. We're splitting it into 75-25. We're again checking our shapes. Then we're going to assign our K values between 1 and 11 and our distance formulas, Euclidean, Manhattan, and Chebyshev. We're going to build our classifiers, our 33 different configurations of classifiers from those, from combinations of these hyperparameters. And then we're going to print our classifiers and make sure they were built correctly. We're going to build our results and run our classifiers to fit the training data to each of the classifiers, which is just memorizing the data. We're going to sort our accuracy results. Once we run the data through the classifiers, we're going to find out our the accuracy score. I used accuracy score. It's more explicit about about using the KNN predict than just score alone, which I just find I just like a little more hands-on approach. So anyway, we've got here sorted all of our accuracy scores, and then we've got things that I was testing and running through to figure things out, blah blah blah. Okay, so now we're plotting. Here is our plot code, and so we've got our training data being plotted here. We've got our which I don't have labeled here, but we've got our test data being plotted here. And we've got our misclassified data plotted here, which the test data, everything that comes up here, that's the test data, which is in these squares. Anything that doesn't have an X over it is classified correctly. Anything that has an X over it is classified incorrectly. So when you zoom in, you can see that the X, the color of the X represents the class that it predicted, and the color of the square underneath represents the true label. And the boundary behind it represents the decision boundary. And so it's very clear here. Here it is alone without the test samples behind it, so that you can see that it's that based on the training data and the test and the decision boundaries that were created, that the misclassified data points are inside those zones, those decision boundary zones, and we'll talk more about that here in a moment, but let's go back to the code. Okay, so now we're going to plot the decision boundaries just the way that it was asked in the assignment, and that'll come up here in just a moment. But as we're waiting, it looks like this. And we've got our different shapes for the classes of the iris data set, and we've got their decision boundaries behind them and the neighborhood sizes. One thing to note here is that we needed to use the plot 2D classification as opposed to the plot 2D separator that was used in the class example. And when you look at dissect MG-learn, for some reason plot 2D classification is not even listed in here, so I had to do some digging to find that out. And then still taking its sweet little time. Okay, well, Oh, there it goes. Okay, it works. Boom, moving on. Alright, so now we're going to do our 4-feature repeat test. Everything works. This is, the results, the accuracy scores for the 4-feature, and then we're going to come over here to our report. So, getting down here, we've got we've used Euclidean distance, Manhattan distance, and Chebyshev difference. The Minkowski distance is just the generalized formula for all of those. You change the p-value, and it means that it equals one or the other. And you can use that in the KNN as a. You can use those parameters in the KNN classifier, or you can just pass in the name of the distance metric and use auto to figure out what the best algorithm to use is based on that. So I chose to do it this way because I like it to be explicit. And then so when we come down here to the analysis, we see that that the top 3 performing KNN models when used with 2 features all used neighborhood sizes of 4, or all 3 of the every time 4 was the neighborhood size, it was one of the top models. Okay, but the very top model was the Euclidean distance, and Euclidean distance is the most popular distance, so that that checks out. Just slightly higher than Manhattan and Chebyshev, which were identical. When we come down here, we can we look at just the training data here, and I have overlaid it on top of the decision boundaries, so that you can, because the training data is used to generate the decision boundaries, because that's the decision that it's going to make when it looks at unseen data. And that's what I was talking about here. As you can see, okay, so before we move on to that, I want to say that here it shows that the Setosa class was all, when we look at just the test data, or just the test data, all of the test data, the unseen data, the model was able to predict with 100% clarity. And you can see this smooth line of the decision boundary, not a whole lot of crisscross there, but where the accuracy dipped was making the distinction between versicolor and virginica classes. And when we zoom in here, you can, or when you look at it a little bit more bare bones here, you can see that there's quite a bit of overlap and different little pieces and things like that going on. So that's what in all of the misclassified, or right here in the center area where all of that busyness is happening. That indicates that Setosa is linearly distinguishable from these 2 classes, but these 2 classes are not linearly distinguishable from one another. And that suggests that so using 2 features was able to find that linear relationship between those 2, but it wasn't enough to find the relationship between these 2. So that suggests that 4 features may be more beneficial by adding more dimensions to find a nonlinear relationship between these 2 classes. So we come down here and we see our, just the basic, the way that it was asked, but I found it was more beneficial to look at it in these formats, so that's what I did. Okay, going down here to repeating the experiment for 4 features, we find that the accuracy had a significant increase of 13.16% from the highest model to all of the models except for the last 2 in the 4-feature in the 4-feature experiment. So that indicated that it was beneficial to making that distinguishing that line between the versicolor and the virginica, and increasing the complexity to find a more complex boundary between those 2 classes. And but it also indicated, because they're all just across the board, they are all the same high accuracy score, except for these last two, that feature that the feature engineering or the feature quality was more important than either of these two parameters, because they, regardless of whether it was any of the three, distance, or any of the neighborhood sizes 1 to 11, the accuracy score remained high and the same. And so that's basically the conclusion, and that's it, and that's my time. Thank you.